Hi, today's lesson we're going to be looking at circuits. In particular, we're going to be looking at resistors in series, though we'll learn also how to distinguish between resistors in series and resistors in parallel. Okay. We're also going to learn about a concept of equivalent resistance and how we can replace a set of resistors with just a single resistor. Okay, so let's get started. The concept of equivalent resistance is similar to a concept we learned earlier in the year where we took a system of several blocks that were connected together but shared a common acceleration. When they had a common acceleration, we could treat these three blocks or multiple blocks as a system, and we replaced these blocks with simply a single block with this total mass equivalent to the mass of the three blocks. So what we did was we replaced the three blocks with a single block whose mass was equivalent to 5 plus 2 plus 7, or basically the sum of all the blocks. As long as we didn't care about the forces inside our system, we were okay. Okay, and even when we did, we had additional knowledge that we could use to help solve our problem. And it's the same thing when we come to resistors. Okay, in this case of the blocks, they shared a common acceleration, and once I knew that acceleration, I could use that to solve for the internal forces. When it comes to resistors in series, which is what we have in the lower right hand corner, okay, we will do something almost identical, okay, except instead of acceleration and force, my resistors are going to be sharing a common current. Okay, and I can use that common current to solve for the individual voltage drops associated with each resistor. Okay, so how do I know when my resistors are in series? Okay, resistors are in series when they are connected at simply a single point. Okay, so in this case, my single point is right here between the two. It's just a wire connecting them. Okay, so it's just this wire. Okay, and there is no turns or branches on that wire. Okay, the picture on the bottom, okay, an electron coming in could go this way, or maybe it goes this way. Okay, so electrons have a choice. Okay, this is similar to what happens when you're driving a car. The instant you hit an intersection, you have a choice: go right, go left, or go straight. Okay, and that's a situation that's not in series. When you don't have a choice and you must keep going forward, that's a situation when your resistors are in series. The other ends of the resistor, okay, this end and this end, must also not be connected. Okay, so resistors in parallel is the other situation we're going to see. And it's important to realize it's not a geometrical concept. Yes, my resistors are drawn in parallel in the two examples below, but for resistors to be in parallel, they must be connected electrically on both sides. Okay, so on this side, all I have is a single wire. Okay, it doesn't matter that I have a branch here, okay, but they're connected on that side, and they're also connected on this side. Okay, for resistors in parallel, it doesn't matter that there are branches and turns and intersections associated with the wires, simply that they are connected on both sides. Okay, so in the picture on the right, they're only connected on one side. Okay, this side is not connected, so this set is not in parallel. Okay, there are two rules basically associated with circuits that we use. I am going to simplify these rules so you don't actually have to use them, but you do need to know them. Okay, the first rule is Kirchhoff's junction rule. We'll see the other rule in the next set of slides, which is Kirchhoff's loop rule. Okay, so Kirchhoff's junction rule is basically a restatement of a very strong, very basic concept, and that's conservation of charge. And what conservation of charge effectively says is that charge is not allowed to build up forever anywhere in a circuit, or charge is not allowed to be drained forever anywhere in a circuit. It may build up for a short amount of time or drain for a short amount of time, but it can't go forever. In other words, no matter where you are in your circuit, Okay, for every electron that goes in, there must be an electron that goes out. Okay, so in mathematical terms, current in equals current out. Okay, going back to look at our slides, okay, an electron that comes in through this side must go all the way through the circuit until it comes out the other side. In the instance on the bottom, an electron can come in this way and goes into this point, okay, and it can go out either this way or that way, okay, and that's what makes the one on the bottom not in series, okay. So Kirchhoff's junction rule basically says that current in must equal the current out, no matter where you are in the circuit. Okay. So how do I apply that to resistors in series? Okay. So for resistors in series, the current in each resistor is identical. Okay. So in the picture on the bottom, this is the 12 ohm and the 6 ohm resistor are my original circuit. Okay. And so I basically have an electron coming in through the one side, and it must leave through the other side. Okay, so in this case, they must have the same current, since current is just charge over time. Okay, so the current through the 12 ohm must equal the current through the 6 ohm. And the law of equivalent resistance, or the concept of equivalent resistance, says if the current going through both of those is the same, then the current through my equivalent resistor must be the same. Voltages will be different, okay? The voltage for the 12 ohm or the 6 ohm and the 18 ohm will all be different, but they do share the same current. And that's the most important part about this set of PowerPoints. Understanding that resistors in series, the current must be the same. Okay, so the derivation of the equivalent resistance law. Okay, because Ohm's law says that the voltage difference for a resistor is equal to the current through that resistor times the value of that resistor. Okay, I basically end up with an Ohm's law equation for both of them. V1 equals I1 R1, delta V2 equals I2 R2. If I'm to replace those two with an equivalent resistor, the voltage drop is going to be from end to end. Okay, or basically the sum of my individual voltage drops. Okay, so I end up with this equation that says equivalent resistance is equal to I2 times R2 plus I1 times R1. And then because all my currents are the same, I can basically replace those two resistors with a single resistor that is the sum of the individual resistances. So the equivalent resistance is just R1 plus R2 plus dot, dot, dot. Okay. So here's a slide for practice. Okay. I want you to find or calculate the equivalent resistance for all three of these resistor networks. Okay. A, B, and C. Okay. I will warn you, though, that C is a little bit tricky. So don't worry too much about that. I will talk about this in class. Okay. So just to summarize, okay, resistors in parallel must be connected on both sides. Resistors in series, however, are connected on one side, and where they are connected, you can have no turns or branches. Okay. And this is important now. Resistors in series have the same current, but different voltages. Okay, and that equivalent resistor is the sum of the resistances, and that formula is on our formula sheet. Okay, and the equivalent resistor, so when I've replaced them, that too will have the same current. So this is very similar to when we did the blocks. All the blocks, including the equivalent block, had the same acceleration. Okay, thank you very much.